All right, geometry, this is your very last video, your very last lesson for the 2019-2020 year. Our topic is going to be conditional probability. Conditional probability is the probability that one event will occur given another has already occurred. These are dependent events. Okay, so this is something that we have already talked about in other notes, and what it was is that if you've got multiple events, what was an example that we had done on this? When you're drawing things out of a bag, if you're going to be drawing marbles out of a bag, if you don't replace the marble, so you're going to draw maybe two marbles. If you don't replace a marble back into a bag, the next event, its probability is going to be altered, whether you want the same color marble or you want a different one. The thing is, you got one less marble in there, so that changes the denominator to your fractions. Okay, and that's conditional probability. Examples 2 and 3, I believe, are going to be closer related to that concept. But example number 1 is actually going to tie back to what we did with frequency tables. Right? Frequency tables were a nice graphic that we could put together that helps organize our information, and then we can pull the numbers that we want from it. So we're going to see in this one, it's a good idea to make that. All right, so example number 1. In a survey of pet owners, 45% own a dog, 27% own a cat, and 12% own both. Okay. The 12% is not exclusive to the other groups. Okay, so what that means is that the 12% is somewhere embedded inside of this 45 and the 27. Somehow it's in there. Okay. Once we come across something like this, and you're maybe really thinking about how the survey was conducted, a frequency table is going to be the best way to present this stuff. Okay, so let's think now, as a survey, what the people did that were surveying. They asked people 2 questions. They asked them, do you own a dog? Yes or no. Do you own a cat? Yes or no. Now, yes, at the end of this, some of the data is going to come back and say, oh, there's certain people that own both of them. But they never actually asked that question, well, how many of you own both of them? I suppose they could have, but most likely what they do is they just ask the 2 simple questions, and then they let the data kind of complete itself. Because they wouldn't ask the same question like, well, do you own neither of them? Well, we already know the answer. They would think you're ridiculous asking like, do you own both of them? Because they just answered that first question. Anyhow, getting off track there. Look, we got a table. It makes sense here because there's 2 different questions that you can answer yes or no. Okay, now it's said here that 45% said they own a dog. Okay, so just thinking about that one question here, 45% said that they own a dog. Okay, so what percent don't own dogs? Right, if 45% own dogs, then you need to subtract that from 100%, and that's going to give you 55%. Oh, by the way, I'm putting my totals out here on the side without making the boxes because I think it'll be easier to see the real, raw numbers and well, they're not raw numbers, but the individual percentages for these. So I'll just keep these outside without boxes around them. Anyhow, so these 2 boxes should add up to give you 45. These 2 boxes should add up to give you 55, and then the grand total, of course, would be 100%. Now, I knew the grand total was 100, so that's how I got my 55. All right, let's look at cats. 27% own cats. Okay, so at the end of the column for owning cats is going to be 27. Now, then the difference to 100 needs to be all the people who said, no, I do not own a cat, which is going to be 73. See, that adds up right? Yeah. All right, so numbers in the middle. The 12%. Yeah, this is where I should read it, though. 12% own both. So in the box that's yes, yes, would have been 12% of our data. Okay? Okay, now if you use the rules for the frequency tables, adding across should give you that total. Adding across should give you that total. Adding vertical gives you that total, and then so on throughout the whole thing. So now that we've got all these numbers filled in, you can subtract the 12 from the 45, which is going to give you 33. Okay? You can also subtract the 12 from the 27, which is going to give you 15. And here's the part that looks really cool, and I wanted to do it in this order so you'd see this happen here. Remember, I had that number and I had that number at the beginning, the 45 and the 27, and I had the 12. Okay, so it makes sense that I could subtract these two numbers and get the 33. I can subtract those two numbers and get the 15. It makes sense if it's in the table anyway. But what I want you to understand is I had these three numbers, and I used those to get these numbers. Now, what's really interesting about it is this last box, it should fit perfect in all directions of things, right? I should be able to take 73, subtract the 33, which gives you 40, and see that 15 plus 40 is 55, that everything works out well together. Okay, so with all of that's just me making a frequency table. I haven't even answered a question yet, but you'd get faster at making those anyway. What is the probability that a dog owner also owns a cat? All right, so of the dog owners, you had 45%. 45% of them own, well, 45% people own a dog. Of them, 12% also own cats. So it's 12 out of 45, which is going to give you about 26.7%. Now, by the way, I realize here that those are two numbers that were at the very beginning of the problem, and you're thinking, well, couldn't I just taken those things and divided them? Yes, but I think it's important that we understand the frequency table that goes along with it so you understand why those numbers get pulled together to get that probability. All right, so examples number 2 and 3. Technically, example number 2 is not quite conditional probability because it ends up being an independent setup here. The example number 3 is the conditional probability with the dependent situation going on here. So be advised, this is not really conditional probability, but it's important that you see that one so you understand what the dependent looks like. I did this with the pens and the paper clips problem like earlier, but you get to see it again and hopefully really understand the difference now. Okay, what we have here is a game that has a bunch of little like tiles on it. So you got some dotted ones, you got some dragons, you got some squares. It looks like you have a flower and a couple of birds and maybe some other things I missed here. But overall, we've got 3 by 5, which means we have 15 total tiles here. All right, example 2. You choose a tile at random from the game of tiles. You replace that first tile. So it's like you pick it up and you put it back down. You then choose again. So two events, two fractions. We're going to multiply them together because we want to look at them happening together. What is the probability that you choose a dotted tile and then choose a dragon tile? Okay, so from the dotted, you've got 1, 2, 3, 4 out of 15. But see, you put that tile back into the set. So that means in your next draw, you're going to have 15 again. In this case, you want to draw a dragon. 1, 2, 3 here. Let's make sure I got all those right. We wanted choose a dotted and then a dragon. So 1, 2, 3, 4. 1, 2, 3. Okay. But these are actually independent events because you put the tile back in there. Like this probability, it doesn't change because this happened. Yeah, sure, you pull the dotted one out, but you put it back in there. All right, so these are technically not dependent events. Okay, and then what you do is you multiply across and you get your answer. But a little bit of mental math is kind of helpful here. That actually reduces down to just 1/5. So you get 4 over 75. Or if you want to see it as a percentage, most of the other notes this week have been percents. 4 divided by 75 is going to be about 5.3%. So that works too. Okay, so these are actually independent events because they're replacing. All right, example 3 is the better example of conditional probability with the dependent events. Okay, how does the probability of the last problem change if the first tile is not replaced? Okay, well, the first event is still the first event. You can get 4 out of 15 chance of success on pulling that dotted tile. But then your next event, you want to get a dragon. Now, if you pull the dotted card or tile out, there's still 3 dragons over here. But that dotted tile was never put back in there. It's gone, right? It's just not in there. So now the denominator is a 14. Hence, conditional probability. If this happens, the next probability is not what it would have been on its own. It is now changed, okay? It's dependent on what happened in the first one. For this, luckily here, we still get to do a little bit of reducing. Not that it's super important, but we get 4, and then 5 times 14, I think it's 70. Should be if that's that one. Yeah. All right, just need to make sure I got that right. All right, these are both even numbers, so if you want to continue to reduce, you get 2 over 35. Or we can just divide it up. 35. And you get about 5.7%. So either of those would be acceptable. All right, so let's look at one more thing here, just because I can, and I'm being spontaneous. I want to show you something here that I'm thinking about. That probability turns out to be higher than this one. That it is more likely to not put the tile back in and get what we want. And that, if you really think about it, it'll start to make sense here that if the first event was a success, that we did pull a dotted tile out of it, by not putting that dotted tile back into the set, your odds of getting a dragon tile have increased because you have 1 less tile that's in there. And so this probability right here has now become more likely by not putting that tile back in there. And you ended up getting a slightly larger percent of this happening there. All right, well, that concludes Geometry 2019-2020. Have a great summer.
Hey, puppy.
I'm trying to do my closing here, Fallon.
No.
Hey, shh. Where was I? Oh, do a little bit of thinking. Don't let your brain turn to mush, and get out and get some exercise. We'll see you in the fall. Peace.